Hello everyone, my name is Ibrahim Ozturk, and today I'll be presenting our work on GLane3D, detecting lanes with a graph of 3D keypoints. This is a research conducted by Tog Trudic AI team. Let's start by discussing the challenge we face: extensive variation in lanes. Lanes can vary significantly across different cities and countries, which poses a problem for traditional top-down approaches. These methods rely heavily on learning lane characteristics from training datasets and often struggle with lanes that exhibit previously unseen attributes. To address this, robust generalization is the foremost requirement for 3D lane detection algorithms. Our approach, GLane3D, is designed to overcome these limitations. Now let's dive into our methodology. We propose a bottom-up approach consisting of 4 main stages. First, we have multiple keypoint estimation. Here, keypoint proposals are generated for each lane, allowing multiple keypoints for each lane point. Next is keypoint refinement. The location of keypoints is refined through the lateral offset concept. Then, we have point NMS, where overlapping keypoint proposals are suppressed. Finally, connection probabilities between keypoints are then estimated, and final lanes are generated by applying Dijkstra's shortest path algorithm. Our methodology's main structure includes several key components. First, BEV feature creation. BEV features are created using the inverse perspective method with custom BEV geometry. Next, keypoint anchors. Each grid cell in the BEV is associated with a keypoint anchor, then proposal detection. The anchor keypoints are classified as foreground or background. Then we have multiple keypoint proposal. The proposal detection module selects anchors as proposal keypoints that correspond to the highest scores in the segmentation map. These proposals are constrained to lie within a certain distance from the ground truth lanes. The transformer layer predicts the X offset, Z class label, and connection feature for each keypoint proposal. The application of the X offset aligns keypoints to target positions. Point NMS eliminates redundant keypoints, and connections are estimated with the adjacency matrix. We also use a custom BEV geometry, a specialized anchor distribution, and increased density near the ego vehicle improve lane detection accuracy. In our open lane experiments and results, the GLane3D model consistently outperforms previous state-of-the-art methods. Even with a stricter 0.5 meter matching threshold, GLane3D shows its robustness and achieves the lowest localization errors in all dimensions. When the F1 versus FPS table is examined, the GLane3D Lite model achieves a remarkable 62.2 FPS, surpassing most models in terms of F1 score, making it highly practical for real-time applications. Ablations on OpenLane 300 demonstrates that combining point NMS with multiple keypoint proposals and custom BEV geometry achieves the highest F1 score. However, multiple proposals without point NMS degrade performance. In our cross-dataset experiments, we evaluated models trained on the OpenLane dataset using the Apollo dataset. Top-down approaches like ladder and Perseformer struggle with environment changes, while GLane3D predicts smooth lanes. Quantitative results support the qualitative observations, and the performance gap increases when the distance threshold is set to 0.5 meters. Thank you for your attention.